All right, guys, so today on Regitude 250, I'm going to talk about genetic terminology, just a simple overview of some terms, and then pedigree tables, and then breaking that down into the different genetic patterns and being able to recognize that. So to start with, I picked out some important genetic terms that I thought were good to review. So to start off with, the first one's heteroplasmy. And heteroplasmy is just a mixture of two types of genetic materials. And clinically, it's just seen variable. So hence the word heteroplasmy. Variable expression, this is just going to be the phenotypic severity is going to vary. So the physical appearance as a result of the mutation will vary from person to person. So it won't necessarily be the same, even though it's the same mutation. So that'll be variable expression. Incomplete penetrance is going to be all those that are affected or have inherited the mutated allele are not going to genotypically show it, or those that are not all that are affected by the mutation will necessarily show it phenotypically. So they could still be a carrier or even affected, but not necessarily present the phenotype associated with that mutation. Loss of heterozygosity is going to be when the tumor suppressor gene is mutated, and so therefore the complementary alleles must be deleted or mutated before the cancer develops. We can apply this concept to either a homozygous mutation where both alleles are mutated, or kind of the two-hit hypothesis where you inherit the first mutation and then the second mutation is either somatic or like environmentally induced. A couple more terms. Imprinting. So imprinting is that the phenotype is dependent on whether the mutation comes from the maternal or paternal origin. And this is always associated with Prader-Willi and or Angelman syndrome. So we just want to know that that's imprinting. Pleiotropy is going to be that a single gene can have more than one effect. So Marfan's is an example here. And so if you have your chromosome here, and this entire chromosome is mutated, but the gene has more than one phenotype. So, for example, in Marfan's, you see the dislocated lens, you see arachnodactyly, you see you can see the pescis excavatum, and the weakness in the arteries. And so all those manifest as a result of just a single gene mutation. So I was just going to explain here that on this chromosome, then there can be several different traits, and all these traits represent a different phenotype. Anticipation is the severity of the disease, and it worsens and or the age of the presentation is earlier in each successive generation. So anticipation, and we can allude these anticipation to like diseases like Huntington's. And then last is mosaicism, which indicates the presence of two or more populations of cells within different genotypes in one individual. So this is usually seen in Down syndrome. So that was my quick overview about genetic terms. Did anybody want to add anything or say anything in regards to those, or have any questions?
Just that on your previous slide when you're talking about heteroplasmy, I just wanted to add that it's related specifically to normal and mutated mitochondrial
diseases. Okay. Yep.
DNA. Yeah.
Yes. Good. Thank you. Anything else? All right. So the next thing I wanted to go into is pedigree. So first thing is I kind of have this little algorithm or maybe a simpler version of quickly being able to recognize a pattern if you were presented with a pedigree. And so here it is. The first thing that you want to look at when you're looking at the pedigree is determining whether multiple generations are affected and whether the affected people have an affected parent. So if you see multiple generations affected, it's most likely going to be a dominant inheritance versus if you see skipped generations, then it's most likely going to be a recessive inheritance. So then focusing on the dominance, we need to then determine whether it's autosomal dominant or X-linked dominant. So the next thing you want to consider after you have determined that there are multiple generations affected is whether there is male-to-male transmission. So a father is transmitting to his son. If you see this, then we can determine that this is an autosomal dominant inheritance. If you do not see this, then it's most likely going to be an X-linked dominant disorder. And to verify that, if all affected males are passing on to their daughters, then that will define that it is a X-linked dominant. So I guess it's like an additional thing to reconfirm. And if all affected, so if perhaps, if you see that all males are passing on to daughters, it's also going to reiterate the fact that it cannot be autosomal dominant. So then moving on to determining if you have skipped generations in the pedigree, then we can assume that it's going to be recessive. And now to determine whether it's X-linked or autosomal, we want to determine whether there are mainly males affected. If males are mostly affected within the pedigree, then we can say it's most likely an X-linked recessive disorder. And if we don't, or if we see both male and female affected with skipped generations, then we can, that is a typo. This should be autosomal recessive. Ignore that, recessive. Okay, so that is the end of my algorithm. Does that seem okay so far? Mm-hmm. Okay, so we are going to practice using that algorithm at the end, but before I do so, I wanted to go into just some unique features about each inheritance pattern. So, autosomal dominant. This is going to be usually only one mutant allele is needed in order for the disease to be expressed. And the disease is usually observed in multiple generations. So you're going to see vertical transmission, so up and down transmission in the pedigree. Usually you're not going to see skipped generations. And if you do, it's most likely that there's decreased penetrance occurring. So if you do see skip, that would be the most likely reason why. Males and females are going to be equally affected, hence autosomal. And then male-to-male transmission, as we talked about in the algorithm, is seen. And they are relatively usually going to be like rare diseases. So here, just reiterating that only one mutant allele is needed. Here you can see that we're going to say that the lowercase is normal and then the capital is affected. So the lowercase homozygous is unaffected. However, the capital is going to be the affected. So the chance of being affected overall is then going to be 50%. And like I said earlier, or maybe I didn't say this, but I will say this now, is that typically the homozygous, typically you're not going to see the homozygous, so like big R, because it's probably not even going to be viable. It will be dead in utero. So we most likely see it presented as heterozygous. A few more things was that the common mating pattern is going to be a homozygous normal with a heterozygous affected percent. So the recurrence risk, therefore, is 50%. Usually an affected person has at least one affected parent, so hence the no skip generation seen and the vertical appearance or vertical transmission. Generally, these diseases are going to manifest as non-catalytical structural proteins that are mutated. So that is the typical association with the autosomal dominant inheritance. And then the autosomal dominant inheritance also shows a trend of late onset phenotype, so maybe seen after puberty, versus like autosomal recessive, in which the enzyme is affected, so it's more seen at birth. Occasionally associated with autosomal dominant is incomplete penetrance, and then it is also often pleiotropic. All right. Does anybody have any questions or want to add anything on or correct anything in regards to autosomal dominance before I move on to the next inheritance pattern? Okay, so the next one is autosomal recessive disorders. Here, both are mutant alleles, meaning both are going to be homozygous for the disease in order for it to be expressed. So little r. Or I guess if we were still trying to carry on how I used it previously, in the previous explanation, I guess it would be big R. So it needs to be the affected letter is homozygous. Must inherit one copy of disease causing the allele from each parent, so each parent's a carrier. And then skip generations are seen, and they're typically seen in one generation of a pedigree, or at least one, for sure. Males and females are also equally affected. Male-to-male transmission is possible, but not subjected to or not more diagnostic in terms of using that algorithm. And then the mating pattern here typically seen is homozygous is produced by the union of two heterozygote carrier parents. So therefore the recurrence risk is 25%. And I will pull up the pedigree in a second to express that. A couple more things about the autosomal recessive inheritance is that the affected person most likely, again, both parents are heterozygous carriers, or one parent is heterozygous and the other is homozygous. It is an earlier onset disease that's seen, or diseases, these autosomal recessive diseases are seen earlier in life, often at birth. They do affect the catalytic protein, so enzyme deficiencies is what it's commonly associated with. And then co-sanguinity is sometimes seen in the autosomal recessive inheritance, and that's because closely related ancestors are more likely to have similar genes. So here's the pedigree, and we're saying here that the little r is indicating the carried mutation. Hence, when it is little r, so homozygous, that's the 25% chance. Any questions or anything that anyone wants to add on to autosomal recessive? Okay, X-linked recessive. So as we know, males only have one X chromosome. Hence, if the X chromosome is mutated, then most likely expression is going to occur. On the other hand, females have two X chromosomes. So both chromosomes must be mutated in order for them to express the disease phenotype. And so theoretically, if one X is mutated and the other X is normal, it's not going to manifest the disease. Because as we said, if the offspring is a female, so XX, we're saying that both has to be affected in order for them to show the disease. And then the disease phenotype, so the phenotypical expression or physical expressions, depends on X inactivation in female. So X inactivation could perhaps, if I understand this correctly, save a mutated chromosome by methylating it. It's also like there's this idea of a bar body as well, which is an X that's inactivated, and it's simply just methylating that X chromosome, as simple as that, as being considered inactive. And so if the mutant X is inactivated, then no disease will manifest. However, okay, yeah, sorry. Okay, I was going to say that if, however, okay, so if the inactivation, though, occurs on the normal X, but there's still the other X that's mutated, then the disease is, I guess it'll just be kind of like a carrier, because it's heterozygous at that point. So one's normal, but the other one is affected. So it doesn't necessarily mean the disease will be expressed, but it will be like a carrier. So multiple generations are affected in X-linked recessive. And there's no male-to-male transmission seen, so that can be diagnostic. And sorry, I want to take back that multiple generations are affected. And I would say that you're most likely going to see skipped generations, but my notes are contradicting. So yeah, I would say that the X, sorry, go ahead.
First aid says it skips generations. So.
Okay, perfect. So yeah, I would agree. So ignore what I initially said. Sorry about that. Okay, no male-to-male transmission, and that would be a sort of criteria factor in terms of following an algorithm. And so I have two scenarios here for us to look at. In the first one, we can say that the male is affected with the little x, and then the female is unaffected, homozygous. And so the females are then going to be here carriers. These are going to be, the two female offsprings are going to be carriers. However, here in the second pedigree, the male is completely normal. However, the female is affected. This is supposed to be a lowercase x. Sorry, it's not very enunciated. And we result here with a affected male. The male child is manifesting the disease. Okay, so that's what I have for X-linked recessive. Anybody want to add anything to that? Okay, so X-linked dominant. So here only one mutant X allele is needed for disease expression. Multiple generations are affected, and usually no skip generations are seen. I guess we can say that twice as often seen in females, since females inherit two X chromosomes. Male-to-male transmission is not seen. And the affected male usually passes the trait on to all daughters. And the affected female trait will pass on to both daughters and sons. So they have a 50% chance. So here we're looking at the male being affected and the female being normal. And so the result is going to be, that the female offsprings here are then carriers. And then in the second pedigree, the female is affected and the male is normal. And the result is that one female offspring and the male offspring will be affected. Any questions? Excellent. Okay, so then the last inheritance pattern is mitochondrial. Usually it's only maternally inherited, and all offsprings of an affected female are going to be affected. No offspring of an affected male are affected, and usually seen as neuropathies and myopathies. So also the idea is that the dad's mitochondria during like fertilization and replication, the dad's mitochondria stays outside of the egg during fertilization, hence why the maternal mitochondria is going to be the affected and why she is going to pass on to all children. Okay, so does anybody have any questions about this or want to add anything? Okay. Well, then I have some questions for you guys. Okay, so I wanted to give you guys an idea of how you can utilize the algorithm and whether it works for you. So with that being said, I can walk you through this one and then you guys can kind of try it out more on your own. But this one's kind of unique because here, I guess the first rule is, are multiple generations affected? Yes, we see that. So we're thinking dominant initially. And then we can think about male-to-male transmission, but right off the bat, we're seeing a trend. Does anybody know what's going on in this pedigree?
Looks like a mitochondrial inheritance because
the
mothers are passing it on.
Yep, exactly. So yeah, I guess that's one thing that you're going to have to like watch out for because obviously the algorithm doesn't clarify the mitochondrial. But yep, the mom is passing on to all children in each generation. So this one's mitochondrial. Okay, here we can try it out. So here, do we see multiple generations affected? Yes, so we're thinking something dominant. And then the next question is there male-to-male transmission, meaning, I guess here we have the male affected. Is he transmitting to his male offspring? No, we don't see that. So therefore, it's most likely going to be, it will most likely be an X-linked dominant disorder. And to verify that, does the male pass on to all daughters? And that's, yes, this male is passing on to both daughters. So that's X-linked dominant. Okay, so now you guys try this one.
We have skipped generations.
So we're thinking something recessive.
And only in males.
Right, and so if mostly males only are affected, we're thinking
X-linked recessive.
Yep, X-linked recessive. Good. Okay, this one.
This looks like mom to all her offspring again.
Yep, exactly. And last one.
Are the dots in the female supposed to?
The dots are carriers, so I would say go with who's affected or is manifesting the disease itself.
So, X-linked recessive?
Exactly. Okay, and then I have 2 questions on the genetic term. So here's a description. Can you tell me what the genetic term is? This phenomena can be described as variable phenotypic severity from person to person.
Variable expressivity?
Yep. And then, oh no, what happened? That's weird. It was supposed to be something else. I don't know what happened to that slide. Okay, let me see if I can ask you real quickly. Okay, the question is, this phenomena describes a single gene which has more than one affected phenotype.
Pleiotropy?
Exactly. Good job. All right, guys. Well, that's all I got.